this video, let us see how do we apply and learn the concepts of Thevenin and Norton theorem. And let us also comparatively study the difference between these two theorems with respect to problem and exam point of view. Okay, when the question is asked on Thevenin theorem and Norton theorem, how different are they and what all are similar, you'll be able to understand that from this video. So I am Professor Mohan, Assistant Professor in Department of EEE, SGBIT. So before going to the problem, let us see the definition. So a linear two-terminal network can be replaced by an equivalent circuit consisting of a voltage source in series with resistance, where VTH is called as open circuit voltage at the terminals or at the load terminals, and RTH is also known as input or equivalent resistance at the terminals when the independent sources are turned off. Okay, so whenever we have independent sources, without dependent sources, I would coin them as type 1. And then when we have dependent sources plus independent, so when we have only independent sources, we call this as type 1. So when we have independent plus dependent sources, I coin them as type 2. So type 2 problem is what we'll discuss here. So this is a two-terminal network, can be replaced to Thevenin equivalent, and whatever is the load parameter, we can connect them across and then so find the unknown parameter. What about Norton theorem? Again, a two-terminal network can be replaced by an equivalent circuit consisting of a current source in parallel with an Rn, right? Where In is called as a short circuit current and Rn is as same as Thevenin, as input or equivalent resistance at the terminal when independent sources are turned off. Again, we coin them as type 1 and type 2. Type 1 where we have only independent source, and then type 2 where we have independent plus dependent sources. So here again we'll see with respect to type 2 problems. So as you can see, two terminal where we have In and Rn. So if you convert this to source transformation, you have this as VTH, and in series you will have your resistance. Right, so RTH and Rn both are same, whereas In, how do you find VTH? So VTH is simply In into Rn, right? So by source transformation, we can just simply say that these two are your practical voltage and practical current source. So source transformation can be used only for your practical elements, that is your voltage or current, and so shifting is used for ideal voltage or current source. So let us take a problem here. So here they've asked us to represent in terms of practical voltage source and current source. So let us first solve for voltage source, and then later on we'll see for current source. That is, first let us solve for Thevenin, and then let us see how do we equate these as Norton also. So by Thevenin theorem, as we have seen, we have to find VTH and we have to find what is RTH, where across the load P and Q. So let us call step 1 to find VTH, where assuming plus and minus for P and Q, VTH is voltage up across 6 ohms. So when you observe here through this window, you can find only 6 ohm as your element. So voltage up across 6 is your VTH. Let us apply node voltage analysis, or you can also use mesh. I'll be applying both. However, in exam, use any one method, either mesh or nodal. So first let me apply node voltage analysis. So taking this as ground and this voltage as directly VTH. As we know, voltage across 6 is VTH. So I'm coining this as VTH, as the junction voltage is VTH, not anything else. So we have two branches at VTH. So we know current entering is equal to current leaving, and none of the currents are entering. So all the currents are leaving. Thus VTH minus 6Ix plus 20 whole divided by 4 plus VTH divided by 6. So we have only one unknown variable, that is VTH. Ix we have to replace. So how can we write what is Ix as by nodal? If you see that Ix is given here, this Ix by nodal, it is simply VTH by 6. Substitute this here. So what do we get? So we can write this as minus 20 by 4, which is equal to VTH by 4 minus 6 into VTH by 6 into 4 plus VTH by 6. So your 6 cancels. So we can say this as minus 20 by 4 is equal to, taking VTH common, you'll have 4 inverse minus 4 inverse plus 6 inverse. So plus and minus 4 inverse, they cancel each other. Thus VTH is equal to minus 30 volts. So we have solved by nodal and we have got an answer as minus 30 volt is our VTH. So in exam we can use any method to solve this. So here I'll be showing two methods. One is by nodal and mesh. So let's solve by mesh analysis now to find VTH. So let us assume this mesh. I'll call this as I. And where is VTH? Here. There's voltage of across 6. So we can simply say by mesh V is equal to R into I. I, according to this current direction, we'll have here plus and minus. It matches with your VTH. Thus, it is VTH is equal to positive of R into I. R is 6 and I is what we must find. So by mesh it is minus 6 into Ix plus 6 into I plus 20 plus 4 into I is equal to 0. So you can see we have one unknown variable Ix, right? So we can simply say in this case mesh analysis Ix is simply equal to I, as both are in clockwise direction. Same current flows through in the loop. Thus your equation becomes minus 6I plus 6I plus 20 plus 4 by I is equal to 0. So this per I cancels. So we'll have 4I is equal to minus 20, or I is equal to minus 20 by 4, where I is equal to minus 5 amperes. Thus, substituting the value of I here, what do we get? So we get VTH is equal to 6 into minus 5, which is minus 30 volts, as same as what we have got by node voltage analysis. Now we have solved for step 1. What is step 1? To find VTH, and we have got by mesh and nodal both a same answer, that is minus 30. So now let us do for step 2. Step 2, what we have to find? We have to find RTH. However, how do we find RTH? We have to find ISC. As we are aware, RTH is equal to VTH by ISC, that is R is equal to V by I. So how do we find ISC? So for ISC, what we have to do? So for ISC, we have to short circuit P and Q, and let me find the current going down, and I coin this as ISC. Now, so if you observe here, let me just depict this at this end here. So we have 6 ohm, and we have a short circuit wire which is having 0 ohms. So can I say 6 is actually parallel with 0, and then the R equivalent is 0 ohms. So thus you do not have 6 ohms. The effect of 6 is not there in the circuit. All the current will actually pass through short circuit path and not through 6 ohms. Thus the circuit diagram to find ISC reduces in this syntax. Now, so you can see here what we had. We had Ix, the dependent source, right? The dependent parameters current. Now what is the current flowing in this path? Right? The current flowing in this path is actually 0. So 6 into Ix, which is 0, is 0 volts. And how do we represent 0 volts? I hope you understood. So we have short circuited the dependent voltage source. Why? Because 6 ohms is appearing parallel to the short circuit current ISC. Thus 6 ohms, there's no effect of 6 ohms, and thus there's no flow of current through 6 ohms. Thus your dependent voltage source goes to 0. Now for this circuit diagram is what we must find our ISC. So let's now find ISC. So ISC, it's quite clear. So we can simply say ISC is equal to, we can say minus of 20 by 4. So why minus? If you see, the current is actually flowing in anti-clockwise. But what we have assumed, current from P and P to Q, that is going down. Thus it is minus 5 amperes. This we have got VTH as minus 30 volts, and we have got ISC as minus 5 amps, and by Ohm's law we know R is equal to V by I, that is RTH is equal to VTH by ISC, which is minus 30 by minus 5, which is 6 ohms. So this is your Thevenin equivalent, VTH and RTH, where VTH is equal to minus 30 volts and RTH is equal to 6 ohms. Now, what you have to do for Norton theorem, or what you have to do for an equivalent current source is asked. Let us say the question is asked with respect to only current source, not with respect to voltage source. Right? So you have what are the steps for Thevenin theorem? Thevenin theorem, step 1, you'll be finding with respect to VTH, whereas under Norton theorem, you'll be finding your step 1 as VOC, or in this case as VPQ. The method remains same. So what about step 2? You'll find ISC. What about Norton theorem? Step 2 is simply IN, which is again same. How? You short circuit and then find the current going down as ISC for Thevenin theorem, but for Norton it would be IN. And then how do you find RTH? RTH is V by I, and similarly for Norton theorem, RN is simply VOC by IN. So if you see, both are almost same. And then how do you represent Thevenin equivalent? Thevenin equivalent, you will have a voltage source in series with Thevenin equivalent resistance. If you transform this to current source, or you're not an equivalent, current arrow mark upwards, and then we'll have a resistance in parallel. This is Rn, this is In. So if it's asked for current source, what you can do? You can solve same by Norton. However, do not use the term or variable called VTH. You can use any other parameter or variable to find voltage across the load, and then short circuit current. So V by I, you get what is your RTH. So this is a small comparison to see how these two are different. So it is as same as Thevenin theorem. However, only the variables changes their name. So VTH is open circuit voltage across load. VOC is also same, open circuit voltage across the load. ISC is short circuit current through the load. IN is also short circuit current through the load. So in this way, we can say both theorem are near to same variables. So thank you for watching the video. Please do subscribe to the channel to watch more videos and enhance your knowledge.